What's up? Linear algebra, new day. What did we study yesterday? Well, we learned about a few things. We finished up the section on homogeneous linear systems, and we also started and finished the section on free variables in homogeneous linear systems, right? So free variables in homogeneous linear systems. What was that section about? That was basically about, it was the proofs. It was theorems. It was basically proving that when a homogeneous linear system has any free variables, then the linear system has infinitely many solutions. Beyond that, we can also show that anytime that a homogeneous linear system has more unknowns than equations, well, then it's going to have free variables, which means it has infinitely many solutions. Also, elementary row operations do not change a column of zeros. So if an augmented matrix has a column of zeros, the rightmost column is all zeros. That is a homogeneous linear system, okay? Something else in there. Right. So when we're translating between augmented matrix and linear system back and forth, we're talking the augmented matrix will always have the same amount of rows as equations or more. So greater than or equal to the number of equations of the linear system, because if there's a row of zeros, you don't need to translate that into an equation, because that would just be 0 equals 0, which has no limitations or any consequences on the variables or unknowns, so you can ignore it. So there's always going to be the same amount or more rows as there are equations in the linear system. Okay, we got a little more detailed. It was like the free variable theorem, free variable in homogeneous linear systems theorem. This is basically stating that we can calculate the number of free variables via taking the number of unknowns minus the number of leading ones will give you the number of free variables. Okay. Yeah, I think that's basically everything. I'll find out though. Free variable theorem for homogeneous systems. Right. Number of leading ones in the reduced row echelon form, augmented matrix. We got to remember that. Right. So, okay. So this is only true, like this idea that if there are more unknowns than equations, then the linear system has infinitely many solutions. That's only true for homogeneous linear systems. However, in the future, we're going to prove that if the linear system is consistent and it has more unknowns than equations, then it's going to be infinitely many solutions as well, or have infinitely many solutions as well. Okay. All right. Okay. Oh, wow. Okay. Oh. When a homogeneous linear system has more unknowns than equations, infinitely many solutions. Right. Okay. So in the in the unique situation where there's a homogeneous linear system with two unknowns and two equations, and there's only one solution, the trivial solution, then the lines cross or intersect at the origin. And that's everything from yesterday. Now we're going to start a section called Gaussian elimination and back substitution. So I'm going to be reading this, and then I'll be back to recall. All right, guys. Just finished up that section called Gaussian elimination and back substitution. Basically, when we have small linear systems, those that can be basically done by hand, solved by hand, we will usually use Gauss-Jordan elimination. However, when we have large linear systems in which computers are used to solve them, typically we'll use Gaussian elimination followed by a technique called back substitution. We basically learned how to do back substitution here. And how do you do back substitution? Well, you get it first into the Gaussian elimination, gets the augmented matrix into the reduced echelon form. From there, you translate it back to a linear system. From there, you solve for the leading variables in terms of the free variables. Then from the bottom, starting with the lowest equation, you're going to substitute the leading variable equals whatever up into the next equation. Then you're going to substitute that one back and up into the next one, and you'll probably solve with parametric equations on the by the end. Yeah, I think that's basically that. That's the idea. It's more efficient for computers than Gauss-Jordan. And then we looked at some examples of how to determining number of solutions based on determining number of solutions based on row echelon form. One key takeaway I got was basically if the bottom row in the row echelon form has zeros and then something in the rightmost column, it's going to have no solutions because it's going to be 0 equals something that's not 0. Otherwise, it looks like you kind of have to do some algebra maybe? Actually, no. I think if there's a leading 1 in each row, then it's going to be one unique solution. And then if there's not, then it's, if the bottom row is all zeros, it's probably going to have infinitely many solutions, potentially. That's what my thoughts are right now. Okay, so that's that. We literally have 2 more small sections left. So to finish out 1.2 reading, I'm pretty happy with that. And yeah, I'm gonna go ahead and start reading some more. Probably won't finish today, but looks like we will finish tomorrow. So talk to you in a sec. All right, guys. So we just started this section called some facts about echelon forms. Okay, these are 3 facts that basically they're not going to prove in this book, but you have to know, or you should know, facts. Okay, every matrix, a matrix only has one unique reduced row echelon form. That's the first fact. Second fact, row echelon forms are not unique. However, you can have multiple different types of row echelon forms based on the elementary row operations you perform. All right. 3, although the row echelon forms are not unique and the reduced row echelon form is unique, both or all of these have the same number of 0 rows, that is rows that are all zeros, and the number of leading ones, or in the position of leading ones. Number and position, but number of 0 rows and the positions of the leading ones. Then we got into a bunch of definitions. I didn't get all through the definitions, but we learned about pivot locations are the locations of the leading ones. Pivot columns are the columns that contain the leading ones. Pivot rows are the rows that contain leading ones. And we're going to learn what pivot is tomorrow. It's like a substitution for one of those. But yeah, I didn't get through that. We literally have about a half a page left until we're done with the reading for 1.2, and we're into 1.2 problem set. So, I mean, we made it somehow. I mean, it felt very, very slow at first, and still, I mean, we've still got to watch these proof videos, how to read and do proofs during this problem set, but it feels like we're moving now. I mean, yeah, I'm happy with that. So, all right, I'll talk to you guys later. See you.